Hey, this is Horner, and this is part 3 of Chapter 2 notes. So there's a couple of different types of forces that we deal with in this chapter that are contact forces. One is called the normal force. The normal force basically just means that you have a force coming from a surface, and it's always perpendicular to that surface. So you'll notice that whether it's at an angle or whether it's flat, it's always perpendicular to the surface, and our 90-degree angle will go with that surface itself. So there's the 90-degree angle there. There's the 90-degree angle there, and then here's the other 90-degree angle. So in geometry, that word normal just means perpendicular, and that's where the name comes from. Friction is the other force that we'll talk about, and it is the one that is parallel to the contact force. And there are two different types. There's something called static friction or kinetic or sliding, and I really like the term sliding much better than I like the term kinetic. Kinetic is kind of deceiving. So if something is sliding across the table, we say it has kinetic or sliding friction. And then if it's just sitting still, then we have what we call static friction. So those are the couple of different types. The force that opposes a sliding motion is called friction. So if I'm moving to the right and I'm slowing down, that means that friction is acting to the left. This enables us to walk, drive a car, and do all the other things. If you've ever tried to walk on ice, you know how difficult it is because you really don't have a lot of friction there. Um, this is really due to microscopic little bumps or even in the smoothest surfaces, and we'll kind of look at what those look like here in a second. We did talk about the two types, or static friction, and that is something that occurs before sliding occurs, and then kinetic friction, which happens after sliding occurs. So in general, the kinetic friction is less than or equal to the value for sliding friction. Friction and the normal force. The friction force actually exerts between two surfaces, and it's proportional to the normal force. So the more normal force there is, the more friction that you'll have between a couple of different surfaces. That's why friction on a sloping surface is less than friction on a flat surface, because remember, on a flat surface, if something has a normal force of 650 newtons, it's because its force due to gravity is the same, 650 newtons. But once you put something on an incline, this force becomes smaller and the force due to gravity never changes. So this would be 650 still, but this would be much less than 650 newtons for our normal force. The next one here is just kind of shows you a little more detail on static friction. The value for static friction is always less than or equal to, and then this is called mu. It's a coefficient. This is Greek letter mu. It's got an S as a subscript because it's the coefficient of static friction. And we multiply that times the normal force. So static friction will continue to go up as a force trying to push the object increases, and that is up to a point. Once we hit that point and the object starts to slide, that's where we have kinetic friction. So let's look at static friction. If I have my physics book and I'm trying to push it to the right and it doesn't move, that's because the frictional force to the left is the same. If I apply more force, you'll notice this arrow gets bigger, but so does my friction force. There's a point to where those two become different, where my bigger apply force is bigger than my frictional force, and now we end up with something called kinetic friction. So kinetic friction is equal to mu k times the normal force, so it's the same equation except for this mu is smaller. It's generally less than static friction, which is motionless friction, for most of the surfaces. Coefficient of static friction, if I want to find out what it is, I'll set a block of a material up and then I will increase the angle. Once I hit that angle, I can find out what mu s is. We're actually going to do this in the lab. And we just find the tangent of the angle, and that will give me the coefficient of static friction. If I want to find the coefficient of kinetic friction, I set up a block of one material on an incline made of another one. I increase the angle until it just begins to move. When I get that, then I can find out what the kinetic friction value is by also finding the tangent of the angle. But I have to be tapping on it. In the first one, I'm not going to tap. So we'll do those together so you can kind of see how those two things work. This is example 2.12. In example 2.8, we had a sliding 750 Newton chest. It was moving to the right at a constant velocity by pushing on it with a force of 450. We found out that the contact force in the x direction was negative 450, and for the normal force it was positive 750. So here they want to know what is the coefficient of kinetic friction for the chest floor surface. So to do this one, we know that the force of friction, the kinetic force of friction, is equal to mu k times the normal force. We can solve for the kinetic friction by just rearranging the equation. So mu k is equal to f little k all over our normal force. We said that the force of friction was negative 450 newtons. We're actually going to do the absolute value of that because we don't want it to be negative, because coefficients are always positive for what we're doing here. And then we have the normal force, which is 750 newtons. And that one is positive because it's up. The newtons cross off. I don't worry about the negative, it becomes positive, and I end up with a number of 0.60, and there's no unit here. So that is my coefficient of kinetic friction. So that's how simple that one really is. This will go into a little bit more detail, kind of talk about why it happens, and then we've already done the solution, so we can skip over this slide. Here are those microscopic little things in the surface, and this is really what causes friction. So these are the little high points on molecular bonds between two surfaces, and so you kind of see how they kind of stick together, and that makes that friction. So there's little tiny electromagnetic forces that hold the atoms together, and those are easy to break, but they still provide a little bit of tug, and so you get friction. So let's take a look at this application. What we're doing here is we're thinking about pulling a box, up an incline. And when I do that, I have to think about where my friction is. So I'm applying a force pulling this up to the left, okay? And if it's frictionless, I will not have any friction pulling it down to the right. So instead, you'll notice that I just have this thing being pulled up to the left, and there's no friction at all. Here are all those contact forces that we could kind of look at. So if I want to go through and I want to find out what the force is in the y, so W here, W in the y, I know that that side of the triangle, okay, is the adjacent side. And if it's the adjacent side, I'm going to take the weight, so that's this W times the cosine of my angle, and here they're calling this angle beta. One thing that you have to realize here is that beta, that angle, is equal to theta, which is the angle here. I know when we've done problems, we've basically just said whatever the angle is here for the incline. If I have an object sitting on that incline, when I make an arrow down and then I make my two components, this angle is also the same. So sometimes it's a little easier, but your book prefers to kind of show you this way. So if I want to know what Wy is, Wy here will just be my weight times my cosine of B. Weight here, you'll notice that it is pointing down, so we're going to make it negative. And we said earlier that weight is equal to mg, so this is negative mg times the cosine of theta, where b and theta are the same thing, or phi, sorry. If I want to know what's going on in the x direction, so I've got this side, that is mg, and that is times the sine of our angle. This is going down to the right. We've said that that's positive x, so that's why this one's positive. We know that this is positive y, so negative y, that's why this one was negative. And those are our two components of our weight force, and that's kind of why you see what you do. They've also shown you over on this side where this is the one going down, and then instead of putting one here, they've actually moved it up here, and it's essentially the same thing. They just made it in a different section than what we've been doing in some of the problems that you'll see later. So those are the contact forces. On this next slide, it's the same thing again. They're just showing you now how in the y direction, the normal force points up, it's positive. We can add that to negative mg cosine of that angle, and because they're equal and opposite, the sum of those forces are 0. Same thing in the x direction. So if I'm traveling at a constant velocity, or if I have no movement at all, then the forces there are going to be equal to 0. And so you'll see that same thing here where negative FA, because we said positive x is down the incline, so our applied force here is going to be back up the incline. All right, so let's do a problem here. It says the safe is to be moved up a ramp to a height of 1.5 meters above the floor. In order to do that, it says the mass of the safe is 510. The coefficient of static friction is 0.42. So remember, that's friction when it's not moving. And the coefficient of kinetic friction is 0.33. The ramp has an angle of 15 degrees. They want to know how hard does the movers have to push to start the safe moving up the incline. So that's breaking the static friction. And then for letter B, they want to know what is it that we need to push at in order to maintain a constant speed. So we're just trying to overcome kinetic friction. Notice kinetic friction is going to be smaller than the static friction. That's why it's harder to get something started than it is to continue to push it if it's sliding across the floor. So that's essentially what these couple slides say. So if you want to read those, you can pause this and take a look at those, but I'm going to move on. Here's a diagram kind of all those forces. I'm going to do my own diagram because I think it makes a little bit more sense. So there's my incline. Here is my safe. We know that pointing straight down is going to be the weight of the safe, so we're going to call it mg. We know we are trying to push the safe up this direction, so that's my applied force. And in the opposite direction, I have my force due to friction. Finally, I have my normal force that's pointing up, and so we're going to call it N. I also need to break up my, my mg into components, because what we're going to do here is we're going to say that this is going to be positive y, and then let's go ahead and we're going to make going up the ramp here positive x, because that's the direction of the motion that I want. I'm trying to push it up the ramp. This side of the triangle right here, we know that our angle here is going to be 15 degrees, and so that makes this angle also 15 degrees. So this side of the triangle is going to be mg times the cosine of the angle, and this side's going to be mg times the sine of the angle. So now that I have those two things, we need to first go through and let's solve for this. Remember, what they want us to find here is they want to know how much force is it going to take to get this thing to start sliding up. So in order to find out how hard we have to push with a force to get that to slide up the hill, we need to look at all the forces in that x direction. So we want to find the sum of the forces in the x direction, and we're saying that this is the positive x direction and this is the positive y direction. So our force that we're pushing with is the applied force, so that'd be Fa, and then we need to subtract all of the forces that are going the opposite direction, and that would be the force of static friction, so that would be FFS. But the force of static friction is a little bit more complicated. It actually has a formula, so we're going to say, and these should be equal to 0. Fa here minus, now remember the force of friction, so we're going to say Fs is equal to mu s times n. But we don't know what n is, but we do know what the weight of that safe is, so we can use the mg cosine of the angle for n. So n is equal, actually here, to mg times the cosine of the angle. So Fa is the force that we're trying to apply. We know that we're going to have to now do my Fs, which is mu s times mg cosine of the angle. But if you look, there's also a force due to gravity that is trying to pull that safe back down the hill. So we actually forgot a force here. We actually need to also put minus, and then we're going to put mg sine of the angle. So we're going to subtract off also mg sine of the angle. So there is a force of friction acting down to the left. There's a force due to gravity that is acting in the same x direction, and then we're trying to push it in the opposite direction. So at this point we can just move the FA to the other side. That make everything negative. We can get rid of all the negatives, and the applied force we're going to use to get this thing started is equal to mu s times mg times the cosine of the angle minus plus mg times the sine of the angle. This is positive because remember when we move this over, then everything became positive all the way across. Our mu s here is 0.42. The mass is 510. Gravity is 10. We're going to do cosine of 15 plus, and then we're going to do this again, 510 times the sine of the angle, which we said was 15 degrees. So let's go ahead and do that math, see what we get. And we get about 3389 newtons. And so that's the applied force that we have to have at least. It needs to exceed this actually to get that safe to start moving up the incline. For letter B, the next thing that they want us to do is we need to tell how much force we need in order to maintain that speed up the incline itself. So for this one, we know that we have the force of friction, which is kinetic, is equal to mu k times n, and that's equal to mu k times mg times the cosine of the angle. And remember that comes from our diagram here. So we've got mg cosine of the angle, which is the same thing basically as the normal force. We still have mg sine of the angle going down the hill. This is mg here. And then we have, we're pushing it up the hill, so this is that applied force. And then we have the kinetic force of friction, so Fk, pointing down the hill. So we know what Fk is. We also need to find out what are the sum of the forces in the x direction. So that would be the applied force that we're using. We've got that plus, let's see, so we've got that, and that is the applied force. We need to now subtract off the force due to friction, and we have to subtract off mg times the sine of the angle. So we can move everything over. Now we're going to say that the applied force is equal to Fk, which we said was mu k times mg times the cosine of the angle, plus mg times the sine of the angle. Because both friction and the force down the hill are going in the same direction, so we actually add those. Now if I want to, I'm going to go through and go ahead and plug everything in. We said that this new coefficient is 0.33, so this would be times 5100 for m times g, cosine of the angle, which is 15 degrees, plus, and then this quantity, which is 5100 times the sine of 15 degrees. So let's go ahead and solve for that and see what we end up with. And we get about 2945 newtons in order to maintain that, velocity moving up the ramp. So notice that this is significantly smaller than what we had before. I think before we had about 3,389 newtons in order to get it moving, but once we got it moving, we only have to apply a force of 2945 to continue it moving up that hill. So that makes it a lot easier to go through and do. And that is the end of this section.